If anybody else wants to record it, let me know. And I'll make it, because I encourage you to record it and put it on YouTube or make a copy for yourself, because remember this much. Zoom stuff will be rewritten over, all right? I got lectures on YouTube that are 10, 12 years ago of mine that students still refer to, and I prefer you have that, or put it on your own computer. Make a copy. I encourage that. Back to this thing. Now that I've showed you, I let the cat out of the bag. If you have your books, here's how we do it. We say that H in general, they wanted H, that's equal to 1 over the intrinsic impedance. I did cover the intrinsic impedance, didn't I, guys? Right? Yeah. 1 over the intrinsic impedance of the region. Then it's going to be a unit vector in the direction of propagation crossed into the E field. That's how you get the H field. We'll do that one. By the same token, if you have the H field and you want the E field, it would be equal to minus eta, that's the intrinsic impedance, times the unit vector in the direction of propagation crossed into the H field. Now these two are essential. And if you remind me, I'll provide those for you on a quiz. I don't usually do that, but I think until you get real familiar with it, I'm going to do that. Now, here we go. We had, for our case, we had the E field, that's the vector phasor form, was equal to 5, right, times e to the minus j. And I think it was 3, right? Was it 3? I'm trying to remember now. 3ax minus 2ay, right? Or 3x, pardon me, times e to the plus j2y az. Do you agree with that, everyone? Right? We have a unit vector of propagation equal to 1 over the square root of 13, and it's equal to plus 3ax minus 2ay. And now if we want h, this is the vector phasor point, I have 1 over eta. Does it say this is in what media? Let me just tell you one.
It doesn't really specify, but in my solutions, it says we assume it's non-magnetic.
It isn't, but I want to show you a few things. Can you all see this right here? I hope you can. You all see this right here? Now, is there an e to the minus alpha anything there? Is there e to the minus like 5z2y anything? No. You can see that there's no exponential decay, so it is lossless, number one. Do you all see that? And if it's lossless, the next thing we can do is find out what the value of mu and epsilon are. And he says non-magnetic. Are you ready to see how? All right, here's how. This problem has got everything in it and more. So we know that gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. And that's equal to alpha plus j beta, right? Everybody? Now, it's lossless. There is no attenuation. So what that means is there is no sigma. With me? Sigma is a conductivity. It has to do with current flow and energy. Really, it's an energy. It's a transducer type effect. It takes electromagnetic current flowing and turns it into heat. There's nothing there that's going to cause loss. That means this term right here becomes just j beta, and that's equal to simply j omega times square root of mu epsilon for lossless. Do you follow me? This will bother some of you, but hang on there. So if that's the case, then we find out that beta and write this down. This is for a lossless region, is equal to omega times square root of mu epsilon. Okay? Now, if beta is equal to this and it is non-magnetic, it means mu is mu zero. Agree? And I can say that this is equal to omega times square root of mu zero epsilon zero times square root of epsilon relative. And that's beta. Agree? And now I can find epsilon relative. I can say that epsilon relative, I'll square both sides. And I'm trying to find epsilon relative here. I got the square root of epsilon relative. Let me do it this way. I'll take square root of epsilon relative will be equal to beta over omega times square root of mu naught epsilon naught. Are you with me? I'm just rearranging. That's square root of epsilon relative. Now follow me on this. Beta is square root of 13, right? Omega is pi times 10 to the 6th. Does anybody remember what 1 over the square root of mu naught epsilon is? It's a very famous term. Anybody at all? Unmute yourself, please, if you're going to talk.
The propagation velocity.
Say that aloud. Say that again.
The propagation velocity.
Yeah, but there's a more fun. It's absolutely true. This is the speed of light, c. It's 3 times 10 to the 8th meters per second. It's an extremely important constant to know. And as an electrical engineer, if you're asked about it, you should respond very quickly. Are you with me? So it's the speed of light, but in a vacuum or in free space. And that is a constant in all reference frames. More on that later. It is an amazing fact. So that's the speed of light. What I mean to say is this right here, 1 over the square root of mu epsilon, I can just put down as 3 times 10 to the 8th on top. That's not exact, but it's very close. With me? The measured value is very, 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 very slightly off. Now, if you take a look, that's equal to the square root of epsilon relative, and that means I can find epsilon relative by squaring this. And what I'll do is cut it down a little. So if I take epsilon relative here and I square both sides, here I'm going to get 13, right? And then if I look at this, well, I have 10 to the 8th, 10 to the 6th. That's really 10 squared. If I square that, I have 10 to the 4th. And then I have 3 squared, or 9 over pi squared. And that would be epsilon relative. Do you agree with me? I feel the same way, Todd. Are you with me on this? Now, what's the value going to be? Anyone? Where's my octaves over here? I'm doing it in octave real quick. Times 9. Did you get a large number? Let's see what it says here. I think this problem is a goofy problem here because I'm getting a phase velocity that's orders and orders of magnitude. I got a value of about 118,000 for epsilon relative. Did you
That's
all?
what I got. But then, so I did it two ways. I did it without squaring everything, and then I did it with squaring everything. And I think you have to take the square root of your final answer because you squared both sides. So that's your answer squared, I think.
No, this is epsilon relative though, right? Isn't this correct?
Your OneNote screen is in the way.
Oh, I'm so sorry. Yeah. If you look here, I'm sorry about that. This is true, right? This. You see it, Jack? That's true. So I'm after square root of epsilon rel. It would be beta over omega square root of epsilon mu naught epsilon rel. So beta is square root of 13, right? Omega is pi times 10 to the 6th, right?
Yeah, I see what you're doing now.
And then this square root of mu epsilon is 3 times 10 to the 8th up here, right? 10 to the 6th, 10 to the 8th is just 10 squared. Y'all agree with me? Take that quantity, that square root of epsilon relative. I need to square it. Square root of 13, 13. Square 3, get 9. 10 squared is 10 to the 4th. Pi squared. I get an answer that's huge. And I think Wentworth just created this problem. It's not based on anything physically realizable. Okay. So that's it. Nevertheless, we have to get eta, correct, class? This is what we need. What's eta going to be? And I'll put it here. Eta itself. Now let me write this down. Guys, I'm over by a minute. Now, I want to say this to the class. If you need to go, go. But now it's an office hour. Is that fair with everybody? This is the first whack at this, and it wasn't planned in advance. So if you need, how many have a class right after this one? Just show me. Could you give me some indication? Ashley, do you have one right now? What, Tyler, what time? Is it right after this?
I have work at BK at 1 o'clock.
Well, you got to go then, buddy, because it's 12:52. You got to go. But this recording will last. Anybody else have a class or a job or something like that? Nobody? Didn't somebody else have it? I wish you wouldn't put it in chat because this doesn't pop up for me. Can somebody tell me what's in chat? Just briefly.
There's nothing in chat.
Oh, excellent. It's even better. All right. If you got to go, you got to go. But for eta, remember, I put it down. If you got to go, this will be available. All right. And I hopefully will be back in person. It'll be a lot better. But eta itself is J, right? Omega mu over sigma plus J omega epsilon. That's the general form, isn't it? Remember, if you don't remember it real well, just realize this is what I developed last time. Now, sigma was 0. That means eta for a loss region over epsilon, or it's the square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. Now, the only thing I'm doing here, and Tyler, I don't want to get you late for your job. So if you got to go, scram, really. I'm serious. All right.
Thank you.
Sure. But y'all agree that that would be the case for a lossless media. Agreed, class? Now, look here. This square root of mu naught is a very famous constant. It's called the intrinsic impedance or characteristic of impedance of free space. It's termed eta naught, and it's really equal to 120 pi ohms or about 377 ohms. So this equation, eta for a lossless region, is equal to 120 pi ohms times square root of mu relative over epsilon relative. In our case, epsilon relative is 1. I mean, mu relative is 1, but epsilon relative is huge. It's equal to 118,500. Matter of fact, let me do this. Let me go ahead and just take the square root of that or I'll get epsilon relative itself here. For this one right here, you find that eta itself you can't see this and I'll show you in a second, is equal to 120 pi times or divided by SQRT of epsilon relative. So I got eta of 1. Did you get that? And by the way, that's ridiculously small. You check me. I think that's the reason Whitworth did this. He chose eta as 1, and this is the result. Okay? So if eta is 1 here, then here's what happens. Now, we're going to just assume eta in our case is 1, which is extremely small. And what that tells you is what? When I go ahead and I get the H field, it's 1 over eta, 1 over 1, unit vector in the direction of propagation, right? Well, that's going to be equal to 1 over the square root of 13 times 3ax minus 2ay, right? Crossed into the E field. And the E field is in the AZ direction. Let me do this on the next page. Can you all hold on for 1 second? I hear people jumping off, but just bear with me. So if I do this, now I come out here and I get the H field as 1 over eta. Eta is 1. Unit vector in the direction of propagation, which is going to be 3ax minus 2ay over the square root of 13. And now this is crossed into the E field, which is 5e to the minus j 3x e to the plus j 2y az. And now I find the H field. Since eta is 1, it's equal to just 5 over the square root of 13 here. Then I take ax, right? And I have to cross it with az. And what's that going to be? X crossed z is, anybody? Minus ay, isn't it? Minus ay, right? And then it's going to be, and that's going to be times 3, by the way. And then I have minus 2ay crossed az. Well, yz is x, so it's going to be minus 2ax here. And then I have to put down the e to the minus j 3x times e to the j 2y. And that's the vector phasor for H. Right there. This coefficient should be out in front. Now, you all see right here, I've got coefficients in terms of x and y. Usually you take the coefficients out in front. But I have 2 components here, right? Y'all see that? The H field now has 2 vector components. And if you look at his answers, or once I give you the PDF of this, you're going to see something amazing. It does, in fact, have 2 components. And can I make this bigger? I think I can. If you look here, you see how this H field of his has 2 components. They're both negative out in front, the coefficients. Y'all see that? Let me make a final statement on this one. The vector direction of propagation is the same in the argument of the cosine internal to both of these will be the same when we go from phasor to time. Make sense? I know I'm taxing you a little. You with me? So the reason this problem, and I'm so glad Tyler asked about this, is essential, is it identifies how to find a vector direction when you have both x and y, z coordinates involved in the argument of the cosine. It shows you also how to identify epsilon relative if it's lossless from beta. You can also get it from the phase velocity, but here I'm just wanted to do it the way I did it. It shows you this equation. I showed you the power, how to find power, right, class? How many are hanging on okay right now? Why don't you take thank you, Ashlyn, and the guys with your cameras on, you okay, William? All right, and somebody had to go, I think Ben had to go. And as far as the rest of you, Lydia, Rafang, Logan, Connor, and Siko, are you guys okay right now?
Yeah, I'm good.
All right. Take a breath here because we're over. Now you have to understand, whenever I do lectures online like this, I assume a few technical glitches, things like that. I'm trying my best here to answer your questions in a timely way. But this problem is so rich in things, and I springboarded into power, right? Let me do one other thing with power. Are you ready? Just hang on. I know it's Friday. All right. And I know you got the weekend, but just hang on with me. Do we have a ball game by the basketball game this weekend or no? Anybody know? Is there any event this weekend besides the playoffs in the NFL that is overwhelmingly interesting to all? Nothing. All right, that's all right. And we don't have class Monday, do we? Or do we?
No
No
class
class.
Monday.
Yeah, and that's the thing I didn't announce. No class, which is another good thing because I'm sure I'll feel better. So we can meet in person Wednesday, God willing. All right, follow me on this. So we're down to this point. Now, here's the thing about power. Please catch me on this one. And some of you are going to say, well, where does this come from? Let me ask you this. If I have an element in circuits, right? If I have a current I flowing through there, and it develops a voltage V across there.
Dr. Baginski, it's on your OneNote. We can't see what you're
I'm
writing right now.
You know, thank you. I got to be more cognizant of the fact that this is, if I have I going in here, and this is a voltage V, and this is some unknown element. Now, you all have had circuits, and you probably work with this stuff more than just circuits, right? If I have this, what is the power associated, average power, from Gross's class or from circuits or from any of those things? What's power always going to be?
IV.
That's V times I in general, right? No vector direction. That's sort of true. This is not quite true. What's the real way to do it? If you wanted average power, it would be 1/2, right? Then would be the real part of V times I conjugated. Do you remember that from Gross's course or any of that? It's V times I conjugate. And the 1/2 comes in because the V and the I are peak quantities, not RMS quantities. Remember that, guys? The units of power are watts, aren't they? Now, when we are talking about average power, we're talking about electric fields, the power itself will be in watts, but it'll be a density, so it'll be per meter squared. So when we talk about the average power flowing, and this is true for a propagating wave, it would be 1/2 the real part of the vector component of E cross the vector component of H vector conjugated. Now this will give you the vector of propagation as well. E cross H will be in the direction of propagation, but be weighted by a big constant. So this is how you get the average power. Now I'm going to take it and make it easy to do. If you go ahead and put in E, remember H and E are intimately linked. You can't separate them. You have an E field that's linked to the H field for the propagating wave. Are you with me on this, class? This is not near field phenomenology. We're talking about a launch propagating wave. When you do this and turn the crank, I usually do this in class. I'm not going to do it here because I'm already over, but this is an office hour. You get 1/2 the magnitude of the E field. This is a nice formula to remember and use. And then you have the magnitude of eta, because eta itself could have an imaginary component. Then you have e to the -2 alpha z, and this is assuming it's propagating in the z direction. So I want to tell you, I'm using this out of Wentworth's book. And in general, I don't give you any problems where energy is propagating in like an X and a Y direction, like problem 6, 7, I would not ask you for the power. I could related to that because it gets a little hairy right now. You're just being introduced to it. So I'm assuming the E field's propagating the Z direction here, just like his book does. And then it would be the cosine of the angle, phase angle associated with eta. Now it's important you understand that phase angle has to do with the angle associated with the intrinsic impedance. And then it would be in a unit vector or in the direction of propagation. That would be the average power flow. I'll do that again, but I wanted you to have that, and here's why. What I'm going to do next time is talk about sections 6.2, 6.3, and 6.4. All these are linked together. Dielectrics, good conductors, and charge-free media, and even 6.5, the Poynting theorem. This is what I'm showing you is called the Poynting vector theorem. And I think I'm going to do a lot more problems that'll be simpler, but I'm going to go through this next time. And really at this point, I know we spent a lot of time on that one problem, but it was so valuable to do because it answers so many questions. This is in your book, and I'll give you the page number. Let me show you this. On page 344 here, you can see what I put down earlier. Then I want to show you the real one. Here, that's the formula I just put down. You see how he has P av equal to magnitude of E squared over magnitude of eta minus 2 alpha Z cosine of the angle associated with eta in the AZ direction. Here he's assuming it's propagating in the AZ direction, and the E field has only an X component. We can open that up and we can make it more general, but this for now is good enough. And he got it from doing E cross H conjugate right here. Everybody see that okay? And thank you for hanging on this long, guys, really seriously. Now, what I'm going to tell you about, polarization is easy. It's next there. And a lot of this stuff back here I'm going to cover. I'm going to give you a reading assignment this weekend, if you don't mind. I know you have Monday off, and I really don't like to be messing with holidays and homework, but I'm going to ask you to do a little bit for me, all right? Now, do you guys have any questions, comments? And did you understand the way I taught this lecture? Was it okay?
Reading the notes was a lot easier this way.
Did you like this way?
Yes.
Was it okay? Jack, was it okay for you?
Yeah, it was good. I mean, there's pros and cons to both, I guess.
I like being in person. I can see you for starters. Second, I can put boxed off equations in a corner and read from, go to them. And I can draw three-dimensional drawings sketches very easy. My handwriting's better to see, even though it's a rotten board. Ben, did you see this okay?
Yeah, I saw it okay. I'd say it was a little easier to see in this setup, but the other one was okay.
I appreciate
just sometimes
that.
glare on the board and stuff.
Yeah. Maybe I'll work on my handwriting. I don't know what to do sometimes. Look, I want you all to stay safe this weekend. And here's one of the things I'm going to just level with you. Now, there are students that are positive that I'm finding out about. It's inevitable you're going to expose yourself to COVID just running around the halls. I mean, there's somebody around there that may have it. I'm not saying you're going to get it, but let's face it, in a campus this large, if you go to a grocery store, probably there's somebody in there that's got it, doesn't know they have it, or they're not saying. So what I'm going to say is, if you feel sick, ill, have a fever of any type, please go get tested. And if you would mind, inform me also if you happen to be one of the unlucky people that have this thing. And there's these regulations called HIPAA rules that are federal that prevent me from identifying a person or anything like that. But let's just go on the assumption that there's always people that's got COVID in your environment. So always be careful and do your best to stay away from people. By the way, William, are you up there in Brown or where are you?
Yes, I'm in Brown right now.
Crowded right now or not?
In between classes, yeah, it's pretty crowded.
All right. My advice to everybody is try to stay safe this weekend. I know it's very hard not to go into restaurants and bars and stuff like that and socialize, but at least for the first 2 weeks, try to let this thing die out. There's people that are positive. Last thing, I'll take, since this is my official and first office hour, I'll take any questions you have. They can, I mean, related to the course.
One I had in the reading that you assigned last time, it's on page 346 and then goes on to 347.
Okay, let me
For
show
Ju-
everybody because some people might not have their book. And I hope you can see it okay. This is 346 right here.
And it's the drill 6.9.
Okay. At the surface of a thick slab, we have an E field here. Determine, okay, E, H, and P. So he wants this. I'll show you what this has to do with. But first, if you look back here in the prior stuff, this is Poynting vector and power transmission. So you guys you don't mind working through this or seeing how it's done, everybody? I got to show you a few things. All right, I'm trying to make sure everybody can see this okay. So here is the drill. I can blow this up if I need to. I hear people dropping off and I don't blame them. So we don't have a ball game then?
We do actually tomorrow against Kentucky.
Here or in Kentucky?
Let me.
Kentucky is the big, I mean, that's always the big game in the SEC is Kentucky. It doesn't matter if you're Tennessee or Alabama. They're the monster usually. With North Carolina, with Kentucky. Is Calipari still there or not?
Yeah,
Yeah. We do have Bruce, so who knows? Maybe, is it here or not?
yeah, it's here.
Let's take a look at this. Is a weird one, isn't it? Look what he gives you. He gives you an E field, at least the one I'm looking at here, is going to be equal to 10 times cosine of 3 pi times 10 to the 7th t ay. And he says that sigma is 10 to the minus 16th. Epsilon relative is 2.56. And it's for z greater than 0. Okay. He's saying that's what the field value is at z. He should say z equals 0. Here's the problem. This is at z equals 0. He doesn't state that in the problem. At least I don't see it. In the problem, he says, huh?
On the second page.
Is it there? It says
Yeah.
determine z for z greater than 0, but they
For
don't
z
say that that's at z equals 0. Oh, yeah, it does. It does. I'm sorry. So that's at z equals 0. So beta z doesn't appear, does it? Follow me, class? All right, but we can get beta. We can say if that's given, we can get beta. And we can get beta by a couple of ways. Well, if you look at this equation right here, he gives you these values. And what else does he say? Anything about mu? All right, look, here's how we do this problem. First, you all agree that omega for this problem would be 3 pi times 10 to the 7th. That would be omega. Agreed, class? by inspection, correct? Next thing, when we look at this, if we have omega and we have these values, epsilon relative is 256. The next thing we can get is beta. First of all, when we look at beta, really what we do is look at gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. Do y'all agree with that? Right? Can you see it, Ben? All right, now watch. If we have this, I'm just looking at something. If we have this, we can say gamma is equal to the square root. Remember, he identifies the material as polystyrene. So it's non-magnetic. I would be j omega. My omega is this. I'm going to leave it as omega times mu, which is mu naught. And mu naught here is equal to 4 pi times 10 to the minus 7th. The units would be henries per meter. Do you all remember 4 pi times 10 to the minus 7th is mu naught? Ashlyn, do you remember, did I teach you this, Ashlyn, or not?
So I know that I remember that from when I remember that from reading the textbook, but I don't remember. Yes, you did go over that on the 13th. You went over.
I don't remember if I went over it in class, but mu naught and epsilon naught are things that you had in EMAG 1, right?
Yes.
Yes.
Okay. All right. So I'm going to just leave it as this for now. It's 4 pi times 10 to the minus 7. Then it's times sigma. Sigma in this case is 10 to the minus 16. I know you want to get up and stretch, walk around. Go ahead if you want to. And then it's going to be plus j omega. Well, omega, I'm just going to leave as omega here. And epsilon. Epsilon relative is 2.56, right? So it's 2.56 times epsilon naught. You can do this. And you're going to get alpha plus j beta. You agree with me, everyone? We got all the values. We got mu naught, got omega, got this. Omega, got that, 2.56. Epsilon naught, I didn't put it down, but epsilon naught is equal to what? You can put 1 over 36 pi times 10 to the minus 9th if you want, but about 8.854 times 10 to the what? Minus 12th farads per meter. Go ahead, I'm sorry.
I was just going to say -12.
I couldn't hear you, William.
I was just going to say -12, but you
Yeah, you're right. You're with me on this? These are constants. They're universal constants. Now, so if that's the case, if I want alpha and beta for this, tell you what, I'm going to actually do this. This reminds me of a problem session that I had. I don't like these on Zoom. I like to be at the board. Let me see if I can get that here. I'm going to just use this, okay? So brought back my screen. I hope you all can see that. And this is, again, this is octave. So I'm going to put epsilon naught is equal to 8.854 times 10 to the minus 9th. And then, oops, sorry. Wrong thing, got to be equal. And then I'm going to say that mu naught is equal to 4 times pi times 1 e to the minus 7th. And let's see, what else? Omega is equal to 3 pi times 10 to the 7th. All right. And sigma, I'll just use sig, equals 1 e to the minus 16th. I think that's everything, isn't it, guys? Right. And now if I go ahead and say what gamma is, would be equal to square root of 1j times omega times mu naught times the quantity sigma plus 1j times omega times 2, I'm just going to put 2.56 here, times epsilon naught. I think that's everything, right? And that's what I got. Do y'all follow me? Connor and Seiko, are you, or y'all see this? Okay, thank you. Yeah, Ashley. Oh, I'm assuming y'all follow me, what I'm doing here, right? Now, once I have that, that means alpha is what? Alpha is equal to real part. I'm not sure if it's just real or what the command is here of gamma. Let me see if that's it. It may not be. You could, and then, yeah, it is. And then beta is equal to the imaginary. Hope that's imaginary part of gamma. Yeah. Got me on that? So I have alpha and beta. Now I can get the phase velocity if I want. It would be omega over beta, right? So that would be the phase velocity if you asked, right? You with me, everyone? Got phase velocity, and he wanted h. Now, technically, h is equal to 1 over 8. By the way, I didn't get eta. What is eta going to be for this one? I'm going to use n. It would be what? Square root of 1j times omega, right? Times mu naught, it's non-magnetic, right? Divided by sigma, right? Plus, sorry, plus 1j times omega times, was it 2.56 epsilon relative times epsilon naught? Everybody agree with that?
Could you just do J times omega times mu all over gamma?
I'm sorry, say that again.
Find eta. Could you just do J times omega times mu over gamma?
But gamma and beta are interrelated, right? Gamma
you
is
can-
alpha plus j beta, right?
Mhm.
All right, this is the way you always get it. You go to the fundamental that has to do with the intrinsic parameters and the frequency, always. Intrinsic parameters are like epsilon, mu, and sigma. Frequency is omega. You got me, everyone, guys? All right, now, once we have this, if we wanted the H field, and here, I'm going to get this out of the way. Oh, thank goodness. All right, I'll leave it. If I wanted the, since I've got those values there, if I want the H field, and I have the E field, right? I have the E field phasor would be equal to 10, and then it would be E to the minus J, or I'm sorry, it would be 10 times E to the minus alpha. I forgot what alpha was. It's small. Let me do it this way. So if you look at this, alpha is this right here. Oops, sorry. That's eta. Alpha is this. It's extremely small. Do you all see that right there? So if that's alpha, whatever that is, I'm just going to leave it as alpha. E to the minus alpha z times e to the minus j. Now beta on this one is actually equal to, right here, is 1.59 about. Do you all see that? Guys?
Isn't it 15.9?
Oh, yeah, I'm sorry. 15.906. Yeah, you're right. I'm sorry. So this is going to be 15.09. I'll leave it as that. Z, right? It's in the AY direction, right?
Dr. Baginski, can you move the octave tab, please?
Yeah, yeah, I can. I'm so sorry. All right. In other words, I didn't put alpha down there. It's very small, but that would be E, right? Just looking at this, the vector direction of propagation is what? Can you see it?
Is it Z?
Isn't it Z, guys? Everyone, take a look. Hang on, guys. Jack, you see that? Ben and Ashlyn and Connor, it's, y'all see that right there? It's just the code. Yeah, the only thing I'm doing is looking right here. It's got 15.09 in front of it. It's got a minus J. It's going in the AZ direction, right? Agree? All right. That means this is equal to AZ. Now, if we want the H field, we've got the E field. We've got beta and everything. It depends if we want to express it as a phasor or time varying phenomena. But to get H, the only thing we do is take 1 over eta. Now, the thing about eta is it's complex, but the angle is about 0. You got a real part that's, I don't know, 16 orders, 17 orders of magnitude larger. For all intents and purposes, it's just the angle there is 0. So it's 1 over eta. Then you're going to have e to the minus, or then you're going to have e naught here. So e naught is 10, right? For this problem, over eta. I'll put in the value of eta is about 7.4459, but we'll put that in there in a second. I can put it in now. So it's 10 over 7.4459, right? That's going to be the magnitude. Then you're going to have e to the minus alpha. I'm just going to leave alpha alone. It's very small. And then e to the minus j, 15.09z. There's more numbers, but that's good enough. And then we have to get a unit vector in the direction of propagation. Now, I want you to watch this. So technically, h is equal to 1 over eta, unit vector in direction of propagation, crossed into the E field. Well, when we look at this, the 1 over eta is a scalar. And then when I look at the rest, the unit vector in the direction of propagation is az. The E field's unit vector is ay, right? And then you would have, of course, the scalar point here, e naught e to the minus j beta z. What is going to be az crossed ay, anyone?
Negative AX.
Right, minus ax. So this is going to be in the minus ax direction. Y'all follow me on that? You guys that are hanging on, Ben and Ashlyn and Sacred, with me? How many see it? Okay. Y'all see it? Okay. All right. Now, this is what I didn't do the math here, but we can do that in a second, right? Can't we, guys? We take a look at what he's got. This was, what problem was that again?
It was a
Drill.
6.
Sorry. Get rid of that thing, yeah. Now, if you look at the drill here, you're going to see that his H field is minus, and he's got minus 42 milli, so this is going to be minus 0.42 actually. And it is in the AX direction, so you're right there, Jack, right? It's got the same cosine phenomenon. We know what beta is. We calculated beta. And he's got beta over here is 0.5. My beta, where's my beta? Is, now I got 15. So I'm not sure if that's wrong or right. That might be incorrect. But the way you get it is the square root of j omega mu times sigma plus j omega epsilon. That will always be the way. He may have a wrong answer here. So if you don't get that, don't worry. And my alpha I got is I got a different value than he did. And I'm not sure, he may have made a mistake here. The frequency was 3 pi times 10 to the 7. There's something, the procedure I did is correct, but he may have something wrong mathematically. And I mean, he may have made a mistake here, and it does happen. I can check on that, Jack. But you follow me the way I did it? Any other questions, guys? You're probably ready to break out of here. Go ahead, William.
On page 325, equation 6.32.
325, did you say?
Yes.
Okay,
Equation.
hold on. 325 equation, say,
Wait, 6.30.
hold on. 325, 6 point,
30.
okay, got it, right here.
So when we're trying to find eta, that's the equation I just said.
Wait. Can you talk a little closer to, I'm hearing a lot of wobble, like a, say it again. This equation
Hear me
right
now,
here?
maybe. Yes, that equation. Using that to
Which equation?
I was using that to find eta.
This?
Yeah, can you not use that to find eta right there? I guess in the problem you can't
Wait,
do it because
you can use this to find eta, but you said beta before.
I'm sorry, I was saying eta, but the mic might be messed up.
Yeah, you can say, sure, you can use it, absolutely.
Okay,
All right,
so in
remember
the
go ahead.
in the problem, that's why I was asking if we could use it.
Yeah.
But okay, cool.
Absolutely.
I'm trying to remember where I even said that, but it's okay.
Yeah, you can use that, absolutely. The problem is gamma requires a calculation most of the time, so it's easier to just do it right here, in my
Okay.
opinion, okay?
I see.
Now, I'm going to give you some more. This is the thing that will save you a lot. Oops. Let me do this. Let me get rid of this thing. Let me do it this way. See those things I circled right here? Both of these two things require you have a direction of propagation. Remember how I showed you to calculate it, okay? Tell you one other thing, since you guys, I've got the last four, and I thank you for holding on. When we're doing propagation through dielectrics, I need to spend a little time on epsilon double prime. Now, in your EMAG 1 course, you should have been exposed to that. That's called the complex dielectric constant. Do you remember that epsilon double prime and mu double prime business or not? It has to do with loss. We'll talk about that. Don't let that give you any heartburn. You see 6.52 here, these formulas? I don't ever use them. That's an approximation. You have calculators that'll take it out to 6, 7 digits, right? Just use your calculators to calculate gamma and you get alpha and beta. Don't worry about this stuff. I don't use it. Nobody does. You follow me? He put it there. When he talks about low loss dielectrics, I'll talk about that in loss tangent. Propagation and conductors we'll go over, but we're going to go through and sort of take care of everything in this chapter thoroughly. But what I want to do is present everything in a way that it shows the linkage between E and H, between eta and gamma, and alpha and beta, and how you apply N power in all the situations, and I'll do my best. Now, any other questions about the homework, guys? Ben, you're up there in Huntsville, right? No?
I'm in Auburn.
Oh, you're in Auburn. I'm sorry. I thought I had somebody in here that was sending me messages. They were, you're remote, aren't you? Or not?
I'm remote.
That's all I need to know more. But I think maybe I don't have one person in Huntsville. Never mind. Anyway, no matter where you are, I hope you got this. Okay. William, did you have any other questions?
No, that was it. I was just like, I crossed it out on my notes. I was like, oh man, I like that formula. But yeah.
No, use it if you want it. Nothing else, Jack? I've had you for at least one class. You had me for
Yeah, I had you for signals last.
Well, signals is a much more abstract type of course. This is more, you can visualize a lot of it. Any other questions before I break it off, guys? Do me a favor, be safe. Keep me informed of any kind of things that I need to know. And do we have a GroupMe page, William, or what do we have going on?
Yes, we have a GroupMe page.
Did you send me? Did you put it in OneNote or not?
It's in OneNote, and I posted it on Canvas as well.
Let me take a look at OneNote, and I appreciate you doing that.
Yeah, no problem.
I don't think I got on it yet.